Okay, so now let's do infinite square well. I got this too. So we talked about stationary states. Now let's do an actual example where we're going to actually start with stationary states. So the example we're going to do is the infinite square well potential. Perhaps this is not the most physical example, but it is pretty important because it's the easiest one to solve, I think, and it's the easiest one to see why the solutions are quantized, and it's just kind of a good test example, I think. I think maybe the classical analog would be, like a perfectly elastic ball bouncing on perfectly elastic walls with no friction, and it bounce between them infinitely without losing any energy. It's a similar thing here. It's like it's a particle basically that's being held in a box of length A by an infinite force. So the potential on the walls of the box, so the walls of the box are infinitely high. So it's an infinitely high potential wall that holds these holds this particle in the box. And the potential inside the box is constant, so the particle is free inside the box, and we might as well make it zero if it's constant. So that's the infinite potential well. You have a potential well of width A, where the potential is zero, your particle is free inside the well, and then outside the well, there's an infinite force preventing the particle from escaping. And importantly, that will mean the particle actually can't escape. There will be zero probability of observing the particle outside the well. Notably, if you make this potential less than infinity, there will be some probability that your particle will be found outside the well, which is kind of strange. But okay. So I've broken this into three regions. In region 1 and 3, we have v equals infinity. Definitely in those regions, the wave function is going to be 0. And then in region 2, we basically just have a free particle, but it's instead of a free particle just like floating through space with no constraints, it's we can actually normalize the wave function since there's an actual length there. Okay, so let's solve the Schrodinger equation in region 2, because we know in region 1 and 3 it's 0. So in region 2, the potential is 0. So the Schrodinger equation just reads h squared over 2m partial squared psi over partial x squared equals e psi. And then if we have a separable solution, the partial derivative becomes a total derivative, and we split it up into, we solve for t of t like we did before. The t is going to be the same thing. T of t is as always going to be e to the minus IE t over h bar. And then little psi of t is going to be the solution to this time independent Schrodinger equation with v equals 0. So in this case, the Hamiltonian is literally basically just a second partial derivative or second total derivative operator. And then this is an ordinary differential equation that we know how to solve, because it's something of the form psi double prime plus k squared psi equals 0, where our k in this instance happens to be the square root of 2me over h bar squared. And we know, either we know or like me, we don't know, and you can look up on Symbolab. The solution to this differential equation is complex exponentials. So some constant times e to the minus ikx, and some constant times e to the ikx. So that's the general solution to this ODE. And then to get the particular solution, we just use the boundary conditions. And the boundary conditions are the constraints on the wave function. So since the wave function is supposed to be continuous, in particular, it's got to be continuous at the boundary of region 2, which is at 0. So since the wave function is 0 in region 1, it's got to be 0 at the edge of region 2 as well. So that means psi of 0 should be 0. which means if I plug 0 in here, I should just get a plus b, so that should be 0. A plus b equals 0, or a equals minus b. Okay, so that's easy. Then I have, if I replace b with minus a, I can also impose the condition that it's continuous at a, and that means that psi of a should be 0. And then that tells us that a e to the ika minus a e to the minus ika should be 0. And then if I multiply both sides of this equation by e to the ika and factor out an a big A, one of these terms becomes e to the 2 ika, and the other term becomes 1. And so if I assume that the constant a is non-zero, which if it were 0, then the wave function would be 0, so that would be stupid. So a is non-zero. So e to the 2 ika equals 1. And if you remember Euler's formula, that means that ka has to be an integer multiple of pi. And I want you to pause for 1 second here, because this is the super crucial bit of information where we've introduced integers. The quantization gets introduced pretty much whenever you see a little n. Okay, so it happened because the imposition of these boundary conditions, basically. All right, and then one thing I will note is that although any integer will satisfy this equation, actually we can reduce this to be any natural number n. And the reason is, obviously n equals 0 is, that's going to give us the wave function 0. So that's not going to be normalizable. So that won't work. And then n negative, since this equation has a ika and minus ika, minus n is going to give us the same solution as plus n. So we can get all the solutions if we exclude 0 and only look at the positive natural number solutions. Okay, and then since k is n pi over a, and I'll denote this kn since it depends on n, and we defined k as being this coefficient here. We define it as 2me over h bar squared. We get a different energy for each n. So we get an en, which, just solving this equation, is h bar squared kn squared over 2m, and then putting back in the kn. Importantly, there is actually a lowest energy. So this is where it differs a lot from classical mechanics, right? In classical mechanics, the energy of your system is sort of, it can be whatever. It's like a continuous quantity, and it can be like really, really little. It can be as close to 0 as you want. It can be anything between, like, whatever, there aren't discrete energy levels. Here we have, excuse me. Here we have discrete energy levels. Sorry. And we have a lowest energy. So we have the lowest energy we can possibly have is h bar squared pi squared over 2ma squared. And then the next energy up is 4 times bigger. And then the next energy above that is 9 times bigger than E2. And then E4 is 16 times bigger than E3. Or no, sorry. It's 16 times bigger than E1. Excuse me. But yeah, so each energy increases by a factor of n squared from E1. So you get these levels, these energy levels. And that's how we're getting these discrete quantities that people are observing. Okay, and then I trust you to do this exercise, which is just take the solution and normalize to find a. One thing that you might want to do is rewrite the wave function as a sine, because it's an e to the, I don't know if you remember this formula where like sine of x from I don't know how much complex variables you've seen, but if you have sine of x, it's e to the I x minus e to the minus ix over 2I. So this, if I just absorb 2I into the constant a, then what I get is a sine kx or a sine n pi x over a. And then an exercise for you is normalize this, integrate psi n star psi over all space, and you'll find that a equals root 2 over a. Okay, so then we've found our time independent solutions, or these are the eigenstates of the Hamiltonian. And then, right, so the root 2 over a sine n pi x over a. And then, and let's draw them as well. So this is what the time independent eigenstates look like. For when they're real. So I don't need to write real part of psi, I can just write psi. But they're basically just wave modes inside the box with n number of nodes. So psi 1 is just a wave with one node. Psi 2 is just a standing wave with two nodes. Psi 3 has 3 nodes. So yeah, that's what your psi n's look like. And these are just the eigenstates. They're just the time-independent eigenstates. If I want the time-dependent solution, all I have to do is tack on this time-dependent factor, t of t. And t of t, or I guess since this depends on n as well, Tn of t equals e to the I en, where n is the nth energy eigenvalue, t over h bar with a minus sign. And then all I've done is substitute in the expression that we just found for the quantized energy levels. So I just subbed in this whole expression here in for En. Okay, so that's the nth stationary state. Again, the probability density of this is independent of time. And then if you have any wave function, I can write it as a superposition of these eigenstates. So I can find some coefficient Cn, so that if I sum up some infinite series of all of these big psi n's, I get whatever wave function I'm looking for. And this works for any wave function, as long as it's normalizable. So as long as it doesn't blow up at infinity or something like that, or as long as it doesn't have, asymptotes, or as long as it's a good wave function, or what we'll call it's L2, it's integrable over the range 0 to a, I can write it as a linear combination of these big psi n's. And then I guess maybe another important thing to note is that I can write the time independent part of it as a linear combination of the time independent eigenstates. So if I have psi of x0, I just plug in 0 for t. Right, all this is a linear combination of the eigenfunctions, the psi n's, with the same coefficient Cn. Because all I've done is taken out this thing and replaced it with 1, this complex exponential. Okay, so now we've talked about that a little bit. The one thing I want to let's talk about what happens when you look at the system. So the system can be in any superposition of these states, right? So if I just give you any wave function that is under this potential, the infinite square well potential, in general it's a superposition of all of these eigenstates. But then when I measure the system, I actually measure one energy eigenvalue. So like say I measure the energy of the system. I actually find the system in one of these states. So if I measure the energy En, then the state was in the state psi n. So what happens is that measuring the system forces it into one eigenstate, even though before measurement, we say the system is in a superposition, in fact, an infinite superposition of infinitely many different states, these psi n's. So that's sort of the measurement. That's how measurement is working with all of this. Okay. Now, exercise for you is to show that the eigenstates are orthonormal with respect to the inner product that we talked about. So remember, we have where's my pen? Remember, we have an inner product on the space of square integrable functions from 0 to a. Sometimes people draw a line in the middle, sometimes not. Sometimes they use a comma. So if I take two functions that are normalizable, so in other words, their integral from 0 to a is not infinity, then their inner product is f star g. And these should be complex valued functions. So that's the inner product. If I take the inner product of psi m with psi n, I should get delta mn, which recall that's right. If n equals m, then I get 1, and if n is not equal to m, I get 0. So this is basically, these are an orthonormal basis for something. In fact, they're an orthonormal basis for any of the square integrable functions from 0 to a. We won't show that they're a basis because we won't show that they span all of the functions, the L2 functions from 0 to a. But it's very easy to show that they're orthonormal. So that's an exercise for you. I'll just do the integral. See that you get 1. Obviously you get 1 because we normalize the wave function. But see that you get 0 when m is not equal to n. Okay. And then I also said I would show you how to compute the coefficients in the expansion of a wave function. So I give you a wave function. You know that you can write it as some linear combination of these stationary states, psi n's. How do I find the coefficients of that linear combination? We use something called Fourier's trick. So Fourier's trick is, first I write down the equation that expresses psi as a linear combination of the psi n's, and I'm only using the time independent part, because at the end I can just tack on the e to the minus iet over h bar and I'll be good. So I take the time independent psi, I express it as a linear combination of the psi n's, then I multiply by psi m star, and I integrate over all space. In the case of the infinite square well, all space means from 0 to a because it's 0 everywhere else. And then what you find is that because of linearity, this sum and the coefficients jump outside the integral. And what you get is an integral of this integral that you just computed, the inner product of psi m and psi n, which we said is delta mn. And so if I sum over n and I have cn delta mn, this just picks out the n equals m term, and the rest of them are 0. And so to find the cm coefficient, what I do is I take psi and I integrate from 0 to a and multiply by psi m star. In the other order, multiply by psi m star and then integrate. And that's how you find these Fourier coefficients. So I will include an example on the problem sheet of just some random wave function that's square integrable between 0 and a, and I'll ask you to find the coefficients, the Fourier coefficients in this expansion. And then so our final result is, I just replaced cm with this thing, or cn with this thing. So these are the coefficients cn, where psi of x is big psi of x comma 0. So that's it. those are the solutions of the infinite square well. These are the eigenstates. Any wave function can be written as a linear combination of those eigenstates times e to the minus I ent over h bar. Great.